Hello. Hello. So hello dear students, welcome to 𝐂𝐤𝐬𝐿. Today we are going to cover the Laplace transform and its properties in this one short series. Okay. Today we will be covering the Laplace transform and the properties, the basic properties, that is ROCs, and the Laplace transform of some basic signals. Then we will be covering the properties of Laplace transform, and third will be the inverse of the Laplace transform. These three things we will be covering in this lecture. So let's start. What is Laplace transform? So before starting the Laplace transform, we have to understand what is the Fourier transform. What is the frequency analysis of a signal? Suppose xt is any signal. Xt is any signal. Then its frequency analysis is done by the Fourier transform, that is called x omega, and x omega is calculated by minus infinity to infinity xt to the power minus j omega t dt. Okay, so this is the formula for finding the Fourier transform of any signal xt. But here we have to know that this Fourier transform formula is valid only when xt is absolutely integrable. So the condition to apply this formula is that xt should be absolutely integrable. The condition is minus infinity to infinity mod of xt dt is less than infinity. That is, xt should be absolutely integrable. This is the requirement of this formula. Now, if we talk about the Laplace transform, what is Laplace transform? Laplace transform means, this was Fourier transform. Okay, Fourier transform is actually the base for the Laplace transform. It is the base for the Laplace transform. Okay, now if we talk about the Laplace transform, then in the case of the Laplace transform, first of all we have to see what is the variable s. In Laplace transform we have a new variable that is called s, and then we have the case of ROC. So what is s? S is the complex number or complex variable that has two terms, that is sigma and j omega, the real part and the imaginary part, sigma plus j omega. Okay, so the Laplace transform is given by x of s, or it is calculated by x of s is equal to minus infinity to infinity xt e to power minus st dt. So this is the formula of calculating the Laplace transform. But here we have to understand the concept of ROC, that is region of convergence. So what is region of convergence of this signal? So for that, let me tell you a very important point here. That is first of all, let us use this formula and find out the relationship between Laplace transform and Fourier transform. Okay, so we can say that the Laplace transform is equal to minus infinity to infinity xt e to power, now in place of s we will put sigma plus j omega. So we'll get e to power minus sigma t e to power minus j omega t dt. So we can say that, so here we can say that the Laplace transform of xt is equal to Fourier transform of xt e to power minus sigma t. Okay, Laplace transform of signal xt is equals to Fourier transform of this signal, right? If we separate this out, then we'll get this. So Fourier transform of any signal is valid only when it is absolutely integrable. So we can say that this is allowed, or this is applicable. The Fourier transform of this signal is allowed only when this particular signal is absolutely integrable. Okay, so this is absolutely integrable. So we can see that in this we have two variables, that is t and sigma. T is an integration variable, that's okay. Sigma is the variable of Laplace, right? So we can say that Laplace transform of xt is applicable, Laplace transform of xt is applicable only in those locations where this condition is satisfied. Sir, how this relation is being created? We can see that the Laplace transform of xt is equals to Fourier transform of this xt e to power minus sigma t, and xt e to power minus sigma t Fourier transform is valid only when this is absolutely integrable. So we can say that this is the required condition for Laplace transform to exist. This is the required condition for Laplace transform to exist. Okay. Now, this is the required condition for Laplace transform to exist. Okay. Now, so we can say that Laplace transform of xt exists for those values of sigma for those values of sigma where xt e to power minus sigma t is absolutely integrable. Okay, so this is the concept of ROC, and the values of sigma where this is absolutely integrable is called ROC. Okay, values of sigma where xt e to power minus sigma t is absolutely integrable is called ROC. Okay, is called ROC. So these are the things that you have to consider. Okay, so I hope all of you are able to understand these points. Now, let's see some properties of ROC, and first of all, let's see what is right-sided signal. Okay, first of all, we will see the right-sided signal, and then we will see the concept of, or the property of ROC. So what is a right-sided signal? Right-sided signals are those which start from a particular time instant and ends up at t equal to infinity. Okay, so right-sided signals are those right-sided signals are those which start at a particular time instant and end up at t equal to infinity. Okay, start at a particular time instant and end at the particular time t equals to infinity. Okay, so this is a right-sided signal. We can have any example of it. For example, start at a particular time instant and end at infinity. So start at a particular time t naught and end at time infinity. Okay, so this is a right-sided signal. So for example, this is also a right-sided signal. Okay, so we can find out the Laplace transform of this e to power at ut. How to find the Laplace transform? We will apply the formula. What is the formula? Formula is minus infinity to infinity e to power at ut e to power minus st dt. So since here we have a term ut, so the integration will be from 0 to infinity only. Now if we integrate this, we'll get the term that is 1 upon a minus s e to power a minus s into infinity minus 1. Now to get this term to be a finite, this whole expression to be finite, we want that this term to be 0, because e to power infinity can be 0 or it can be infinity. How? Let me tell you. E to power alpha infinity. So this can be infinity or 0 depending on alpha. If alpha is positive, then it is infinity. If alpha is negative, then it is 0. Because if alpha is negative, then this term will be e to power minus infinity. Okay. And if alpha is positive, this term will be e to power infinity, and thus the answer will be infinity. Okay. So we need that this term should have a negative real part. We need that this term should have a negative real part, and thus we want that e to power a minus s should be 0. This is possible only when a minus has as a negative real part. That is, a minus s should have negative real part. Negative real part. So, what is the real part of s? We know that real part of s is sigma. Okay. So, real part of a minus sigma should be less than 0, or we can say that sigma should be greater than real part of a. This is the condition. Okay, this is the condition, and when this condition exists, this term will be 0, and minus 1 will come out of the bracket, and the result will be 1 upon s minus a. And what is the required condition? Sigma should be greater than real part of a. So these are the important conditions. So let me write down the result. This result is very important and you should remember this. So the result is e to power at ut has Laplace transform 1 upon s minus a, and the condition is sigma should be greater than real part of a. Okay, sigma should be greater than the real part of a. This is the condition. So I hope all of you are able to remember this. Everyone is able to remember this condition. Okay, this result is also very important. E to power at ut has Laplace transform 1 upon s minus a, and the ROC or the condition is sigma should be greater than real part of a. Now we can solve all these type of questions. E to power 2t ut is 1 upon s minus 2 and sigma greater than 2. Okay. Third, e to power 3t ut will be 1 upon s minus 3 and sigma greater than 3. All these are right sided signals, right? Because they are starting at t equal to 0, ending at t equal to infinity. E to power minus 2t ut 1 upon s plus 2, sigma greater than minus 2. So these are the conditions and the Laplace transform. So I hope all of you remember this. We'll try to remember this. E to power at ut has Laplace 1 upon s minus a, sigma greater than real part of a. What about this? E to power at. Here a is a complex number, 3 plus 5j. So this is 1 upon s minus 3 plus 5j. Okay. And here we can see that the real part of a is 3. We are concerned about the real part of a only. So sigma greater than real part of a means 3. Okay, sigma greater than real part of a means that is 3. Sigma greater than 3. Now there is one conclusion about the ROC. There is one conclusion about the ROC. What is the conclusion? conclusion about the ROC for the right-sided signals. If the signal is right-sided signal, then there is a conclusion of the for the ROC. From the examples that we have already seen in the previous slides, we can say that before moving to the conclusion, I need to tell you one very important point. What is a pole of a system? What is the pole of a Laplace transform? Pole of a Laplace transform. So, suppose we have xs that is Laplace transform has some numerator and some denominator, Okay, so this numerator and denominator, the roots of the denominator are called poles, the roots of the numerator are called zeros. Roots of the denominator are called poles and roots of the numerator are called zeros. Are called zeros. So we will move on. So suppose for the right-sided signal, we have the ROCs, we have the Laplace transform 1 upon s minus 2 in the previous slide. The ROC was sigma greater than 2. We had the expression 1 upon s minus 3 plus 5j. So we have the ROC sigma greater than 3. So from the previous examples, in all the examples we had the signal that was right-sided signal. In all the cases we can say that the ROC was sigma greater than real part of the pole. Here we can say that the pole location is, pole means the root of the denominator. We can say that the pole is at 3 plus 5j. So ROC is sigma greater than real part of the pole. Are you able to see that? Sigma is greater than real part of the pole. Here we can say that the pole is at 2. So the ROC is sigma greater than 2. Here we have pole is at 3. The ROC is sigma greater than 3. Here we have pole is at minus 2. So ROC is sigma greater than minus 2. Okay. So the conclusion is, the property is for right-sided signals, the ROC of Laplace transform, the ROC of the Laplace transform is sigma greater than real part of the rightmost pole. Real part of the rightmost pole. Okay, so always remember this very important characteristic of the right-sided signal. Okay, now let's move on to the left-sided signal. So first of all, let me define the left-sided signal for you. What is the left-sided signal? The left-sided signals are those which start at t equal to minus infinity and end at a particular time instant. Okay, so right-sided signals are those which start at a particular time instant and okay, we start at minus infinity time and end at a particular time instant. So start at minus infinity and at a particular time instant t naught. So this is a left-sided signal case. Okay. Okay. Now this is also a left-sided signal. We can say u of minus t. This is also left-sided signal. Let us find out the Laplace transform of this. So Laplace transform will be equal to minus infinity से infinity e to power at u of minus t e to power st dt. Okay, so now we can solve this very easily, this integration. Okay, so let us find out the integration. The integration will be from minus infinity to 0 e to power a minus s t dt. Okay. Now in this integration we'll get 1 upon a minus s outside. Okay, and now we'll put the limits. We'll put 0, so we'll get 1. We'll put a minus infinity. Okay, so this is what we are getting. Now this term, okay, so this term we can see that this term has to be 0, otherwise this whole expression will be undefined or it will be infinity. So this term has to be 0. For making this term 0, it is very important that this constant term with infinity is positive, because here we have a minus sign. So this term should have a positive real part. So a minus s should have a positive real part. The real part of this should be positive. So it means that real part of a minus sigma should be positive. So here we can see that sigma should be less than real part of a. And when this condition exists, this term will be 0 and the Laplace transform will be 1 upon a minus s, or we can say minus 1 upon s minus a. Okay. So what is the result that we should remember? The result that we should remember is these two things: the Laplace transform expression and the ROC, the region of convergence. Okay, the condition of sigma. Okay, now let's move on. First of all, let me write the whole relationship. E to power at u of minus t, e to power at u of minus t, okay. So this is the left sided signal and the Laplace transform is 1 minus 1 upon s minus a, and the ROC is sigma less than real part of a. Okay, so using this relationship we can find out the result of this. E to power 2t u of minus t is minus 1 upon s minus 2, sigma less than 2. Okay, great. What about this? Minus 1 upon s minus 3, sigma less than 3. What about the last one? Minus 1 upon s plus 2, sigma less than minus 2. Okay, so remember this result, this is very important. Now what about this? E to power at u of minus t, it is minus 1 upon s minus a. The ROC will be sigma less than 3, real part of this. Okay, so if we look at these three results that we have seen, then we can see that here the pole location is 3 plus 5j and ROC is sigma less than 3. Means we can say that the ROC is sigma less than real part of the pole. Okay, can you see the format of ROC? The format of ROC is sigma less than real part of the pole. Here also we can see that the pole is at 2 and the ROC is sigma less than pole location. Here we can see that the pole is at 3, sigma less than 3. Here we can see that the pole is at minus 2, sigma less than minus 2. These are the conditions and these are the ROCs. Okay, so we can see the condition of ROC. So what is the second conclusion for the ROC? The second conclusion for the ROC is, for the left sided signal, For the left-sided signal, the ROC is of the format sigma less than real part of the pole. Sigma less than real part of the pole, or we can say that sigma less than real part of the leftmost pole. Real part of the leftmost pole. Okay, leftmost pole. For example, in the right sided we had the condition sigma greater than real part of the rightmost pole. Here we have the condition sigma less than real part of the leftmost pole. Okay, now this is a signal which is both sided signal. Both sided signal means for example, we can say this is right sided and this is left sided. So this signal will start from minus infinity, end at plus infinity, because it has both combination, it has both the type of signals. One is right sided, one is left sided. Okay, now first of all let us find out the transform of this transform. So we know what is the transform of this, 1 upon s plus 2 sigma less than minus 2, sorry, sigma greater than plus minus 2, because this is a right sided signal. We have the transform and the location of pole is minus 2. So the ROC is sigma greater than minus 2. The second one plus minus sign 1 upon s minus 2. Okay, is this clear? Yes. So we can see that the pole is at 2, the ROC will be sigma less than 2. Okay, so now we can combine these two. We can say that this requires a condition sigma greater than minus 2, this requires the condition sigma less than 2. So if we combine the two, we'll get the result 1 upon s plus 2 minus 1 upon s minus 2, and the ROC requirement is minus 2 to 2. Okay, minus 2 to 2. I hope all of you are able to do it. This is the complete requirement. Okay, so this is the transform and this is the ROC. So we can see that for the both sided signal, the ROC is between two poles. Two poles means if we draw the S plane, if we draw the poles of this Laplace transform on the S plane, we can see that one pole is at minus 2, one pole is at 2. Okay, okay. So if we draw the poles of this Laplace transform on the S plane, then we can see that there are two poles. One pole is at minus 2, one pole is at 2. So one pole is at 2, one pole is at minus 2. So we can see that the ROC is between the two poles. Okay, for both sided signal, the ROC is between the two poles. For both sided signal, the ROC is between the two poles. Okay, the ROC is between the two poles. Okay, now, so just remember this, I have already told you this. Just remember these two very important results. E to power at means 1 upon s minus a and sigma greater than a. E to power at u of minus t, this is minus 1 upon s minus a sigma less than a, or real part of a. Real part of a. Okay, so these are the things that you can remember. Okay, now let's move on. So the third condition or the third conclusion is for both sided signal. For both sided signal, the condition on the ROC is that ROC is between the two poles. Okay, always. For both sided signal, the ROC is a region in the S plane between the two poles. So for the both sided signal, we have this kind of ROC. The ROC is the region between the two poles in the S plane. Okay, great. Now let's move on to the fourth condition of fourth conclusion of ROC. The fourth very important conclusion of the ROC is that ROC never contain a pole. Okay, ROC never contain a pole. Okay, so the next condition is ROC never contain a pole. Okay, ROC never contain a pole. Great. So the next condition is ROC never contain a pole. Okay, ROC never contain a pole. This is the next condition of the ROC. So we have seen three conditions or three conclusions. One for right sided, for left sided, third for both sided, fourth we have this condition that ROC never contain a pole, and next is for the finite duration signal. Finite duration signal means a signal which start from a particular time instant and end at a particular time instant. Okay, so finite duration signal means they start at a particular time instant and end at a particular time instant. So for the finite duration signals, for a finite duration signal, the ROC is the entire S plane. Always remember this. ROC is the entire S plane. Okay. Always remember this. ROC is the entire S plane for the finite duration signals. Okay. Now, so we can see that ROC is dependent only on two things. ROC is dependent only on two things. One is location of pole, that if the pole is known to us, then we can find out the ROC, but we also need, with the pole, we need the format of the signal, that the signal is right sided, left sided, or what kind of signal is it. So the location of pole, it is dependent on location of pole and next is format of the signal. Format of the signal. Format of the signal means the signal is right sided, left sided, or what kind of signal is it. Okay. So the example of finite duration signal, we can have many examples for finite duration signals. Suppose we have a signal like this. Suppose we have a signal from 0 to 10, height is 5, let us say. So this is your xt. Okay, this is your xt. So let us find out the Laplace transform of this. What is the Laplace transform? The Laplace transform will be, we'll be integrating only from 0 to 10, height is 5, e to power minus st dt. So if we integrate this, we'll put 1 upon s in the denominator, minus 1 upon s in the denominator, and we'll integrate this 5 e to power minus 10s minus 1. So if we just arrange this minus sign inside the expression, we'll get 1 minus okay 5 upon s. So this is the result. Okay, so the ROC will be entire Z S plane, the Laplace plane, because this is a finite duration signal, so we need not worry about the ROC, and this is the Laplace transform of the signal. Okay, so let's find out the Laplace transform of ut. So we know that e to power at ut is having the Laplace transform 1 upon s minus a sigma greater than a. If you put a equal to 0, then this term will convert into ut. Okay. If we put a equal to 0, then this will become ut, and ut will have Laplace transform 1 upon s and sigma greater than 0. Okay. Okay. So this is all for ut, right? Great. Let's move on. The Laplace transform of 1.0. 1.0 means it's a constant DC signal which is from minus infinity to infinity. Okay. Constant DC signal from minus infinity to infinity. It is a constant DC signal from minus infinity to infinity. So we can see that this one can be broken into two parts, that is right sided part and left sided part. This one can be broken into right sided part, that is ut, and the left sided part, that is u of minus t. Okay, this can be broken into right sided part and left sided part, ut and u of minus t. Okay, and now from this setup, let me find out the Laplace transform of u of minus t also. Okay, so ut we have already found. Let us find out the Laplace transform for u of minus t. So u of minus t means we'll write e to power at u of minus t. The Laplace transform will be we can write out the expression. The expression is 1 upon s minus a with the minus sign and sigma less than a, or real part of a. If you put a equal to 0 here, we'll get the result. A equal to 0 means it will be u of minus t, and this will be minus 1 upon s sigma less than 0. So this is the Laplace transform of u of minus t. Okay. Now, if we look at 1 can be written as ut plus u of minus t. This is right sided part, this is left sided part, and now this is 1 upon s. The Laplace transform will be 1 upon s, but ROC requirement is sigma greater than 0. This is minus 1 upon s, ROC requirement is sigma less than 0. So we can see that these two terms cannot be combined together, because this term required the condition sigma greater than 0 and this term required the condition sigma less than 0. We cannot combine them together because there is no common ROC. There is no common region, or where there is no common value of sigma where both Laplace transform exist. So we can say that the Laplace transform of this signal do not exist. The Laplace transform do not exist because there is no common ROC. Okay, we can see that there is no common ROC. Great. So let's move on. So there are many signals for which the Laplace transform cannot be calculated. This is one of those signals. Okay, this is one of those signals. We have many more examples. Okay. Okay, so let's move on. For example, we have one more signal, e to power at. E to power at. E to power at, this is not e to power at ut. This is not e to power at ut. This is e to power at. E to power at means it is a signal from minus infinity to infinity. So again, we'll break it into two parts. e to power at ut, the right side part, and e to power at u of minus t, the left side part. Okay, the ROC of this will be the Laplace transform will be 1 upon s minus a, and the requirement is sigma greater than a. Real part of a or a doesn't matter. We are assuming that a is real here. The ROC of this will be minus 1 upon s minus a, but the ROC will be sigma less than a. So we can see that we cannot combine these two because this term required the ROC sigma greater than a, and this term required the ROC sigma less than a. So we cannot combine these two terms, and thus we can say that Laplace transform do not exist. So always remember that the signals of this format, the DC signals which are constant from minus infinity to infinity, or e to power at, the Laplace transform do not exist. Okay, the Laplace transform do not exist. Great. Okay, perfect. Now let's move on to the properties of the Laplace transform. Properties are very important, and I request all the students to be very attentive while reading the properties. Okay. Great. So let us read all the properties of the Laplace transform. We will see the insight of the properties also. Okay. So first of all, let's see the property, then we'll see the insight of all the properties also. The first property is time reversal. If xt has Laplace transform x of s, then x of minus t will have Laplace transform x of minus s. Okay. If xt has Laplace transform xs, then x of minus t will have Laplace transform x of minus s. Okay. Now the property says that if xt is even, then xt is equals to x of minus t, x of s is equals to x of minus s. Okay, xs is equals to x of minus s. Okay. Similarly, for the odd ones, for the odd also we will have the same property, similar one. The property is if xt is odd, then xt is equals to minus times of x of minus t, so x of s will be equal to minus times of x of minus s. Okay. Okay. So these are the properties. So means this is the time reversal property. This is the property that if xt is even, then Laplace transform is also even. Okay, Laplace transform is also even, and same goes with the odd also. Okay, same goes with the odd. ठीक है, तो ये आ गया. We have got this. If xt is even, the Laplace transform is even. If xt is odd, Laplace transform is odd. Okay. Now, time reversal property has a very important significance. What is the significance? Let us see. Okay, so if xt is even, then Laplace transform has a very important property. Then xs has a property that if there is a pole at P, remember this property always. Okay, this is a very important property, and many a times GATE has asked questions on this property itself. Okay, so if there is a pole at P, then pole at minus P also exists in the Laplace transform. Similarly, if 0 at Z, then 0 at minus z also exist. Okay, so if there is a pole at p, the pole at minus p also exists. If there is a 0 at z, the 0 at minus z also exists. Okay, these are the two important conditions. Now, for odd case, if xt is odd, then Laplace transform will follow these 2 points. Okay, will follow these 2 points. So if xt is even or odd, the Laplace transform will follow these 2 points. Okay, the Laplace transform will follow these 2 points. Okay, but in case of odd, there is one more point or one more property that is followed by the Laplace transform. There is one more property followed by the Laplace transform. So there are 3 points. If pole at p, pole at minus p also exists. If pole at if 0 at z, then 0 at minus z also exist. Okay, so these 2 properties are there, followed by even case and odd case both. But there is one more property followed by the odd one. What? Since we can see that x of s is equals to minus times of x of minus s in case of odd. So if we put s equal to 0, that is origin. S equal to 0 means real part and imaginary part both 0. So we can see that x of 0 will be equal to minus times of x of 0. So we can see that a number is minus times of itself means x0 has to be 0. So x0 is equals to 0, that is 0 at s equals to 0 exist. 0 at s equals to 0 exist. So in these 3 conditions are followed for the odd one, these 2 for the even ones. Okay, so these are very important properties that you have to remember, and many a times direct questions can be asked in this in case of Laplace for even and odd. Okay, great. So let's move on. Great, let's move on. Time reversal property. Now conjugation in time. Conjugation in time property. Conjugation in time property is also important, and its conclusion is also very important. Okay, so the property says that if xt is having Laplace transform x of s, then x conjugate t will have Laplace transform x conjugate s conjugate. Okay, this is the property. Now the conclusion of this property is this. The conclusion of the property is that if xt is real, then Laplace transform, if xt is real, then the Laplace transform xs, Laplace transform xs will have, okay, if xt is real, then Laplace transform xs will have complex roots. Complex roots means complex poles or zeros. Complex poles or zeros in conjugate pairs. In conjugate pairs. Okay, always remember that. If xt is real, then Laplace transform xs will have complex poles or zeros in conjugate pairs. Okay, there is nothing for the real poles or zeros. Only for complex poles and zeros they will be in conjugate pair. Conjugate pair means if there is a pole at, for example, 3 plus 4j, if there is a pole at a plus jb, let us say, then there has to be a pole at a minus jb, that is at the conjugate location. Okay, this is for this property is not very important, but this conclusion is very important. Okay, so we have seen the conclusion for odd case, we have seen the conclusion for even case, we have seen the conclusion for the real case also. Okay, now let's solve some or one or two examples for more clarity. Okay, so if x is even and real, it is given that the signal is real and even, and it has two poles. There is a pole at 3 and 4 plus 3j. Pole at 3 and 4 plus 3j. So now we have to find out the other poles. We have to find out the other poles using the property that xn is even and real. So let us say first of all, let us apply the condition for real. What is the condition for real? The condition for real is the complex poles are in conjugate pairs. Means for real case, 3 will not be affected, 3 will be 3 itself. We will have 4 plus 3j, but we will have one more pole at the conjugate location. We will have one more pole at the conjugate location. Okay, 3, 4 plus 3j and 4 minus 3j. Great. Now this is for the real property. Now we'll do for the even also. Even says that if there is a pole at P, there has to be a pole at minus P. So simply when we apply the even property, then there is a pole at 3, there has to be a pole at minus 3 also. There is a pole at 4 plus 3j, there has to be a pole at minus 4 minus 3j. There is a pole at 4 plus 3, 4 minus 3j, there has to be a pole at minus 4 plus 3j. So this is for the even property. So first of all, we applied the real property. We can apply first even also and then real, doesn't matter. First we apply the real property. Real property means the complex poles will be in pairs, conjugate pairs, and for the even, if there is a pole at P, there has to be a pole at minus P. Pole at P, there has to be at minus P. Pole at P, there has to be at minus P. So we got 6 poles finally in the Laplace transform. Okay, exactly similar condition here. We have the complex pole 3i and 5 plus 8j. Now, first of all, if we apply the real case, now since this is complex or the imaginary pole, this will also go in the conjugate locations. So, for the real condition, the condition will be, we will have the poles at 3i and minus 3i. Okay. For 5 plus 8j, we will have the poles at 5 plus 8j and 5 minus 8j for the real conditions. Okay, real condition means if the pole is complex, then it will be in the conjugate pairs. So we can see the conjugate pairs. Now we apply the condition for even. Even means if there is a pole at P, there has to be at minus P. Okay. Great, this pair. Okay. Now this one, if there is a pole at P, there has to be a minus P. Okay. So if one can think that, sir, there is already a pair. No, we have to create one new pair. We cannot spare them. We have to create one new pair. Okay. So if there is a pole at P, there has to be at minus P. The pair is already there. No, but still we have to create a new pair. Even says that we have to create a new pair. Okay. 5 plus 8j minus 5 minus 8j, and the last is 5 minus 8j minus 5 plus 8j. Okay, so these are the conditions. Okay, so these are the poles that we have got. So total number of poles will be 1 2 3 4 5 6 7 8. 8 poles will be there. Okay, now let us learn all the rest of the properties. Time shifting property. Time shifting property means the effect goes with the same sign. Effect goes with the same sign. So the property says that if xt has Laplace xs, then x of t minus t naught will have Laplace. Okay, so the effect goes with the same sign. If we are shifting by t naught, the effect will go with minus s t naught only. The effect goes with the same sign. T plus t naught means e to power plus s t naught. Effect goes with the same sign. Okay, so always remember that the effect will go with the same sign. Great. So time shifting property is done. Next is time scaling property. Time scaling property says that if xt is having Laplace transform x of s, then x of at will have Laplace transform 1 upon mod a x of s by a. Okay, so this is the property. Okay, next. Now shifting in s domain. Shifting in s domain. Now first of all, let me tell you one very important thing about all these properties. We have to remember that we only need to remember the expression. We only need to remember the expression. We don't need to worry about the ROC. Okay, why? For example, let me tell you. Suppose I have a signal. Suppose I have a signal. So let's see an example. For example, we have e to power 2t ut. The Laplace transform is 1 upon s minus 2 sigma greater than 2. Now if we do the time scaling, so let us say if this is xt, we put x of 2t, let us say x of 2t. X of 2t means in place of t we put 2t. So e to power 4t u of 2t. U of 2t is nothing but ut only. So x, this is this. So here we will do the scaling. So that is, we have put a equal to 2 means 1 upon 2 x of s by 2. X of s by 2 means s by 2 minus 2. And what about the ROC? Don't need to worry about the ROC because this is the right sided signal. We can see the pole location is 4 right now. So this will be sigma greater than 4. Okay, sigma greater than 4. Okay, now this is the ROC. So like this ROC, you don't need to worry because you only need to know the format of the signal, the pole of the Laplace transform. You can find out the ROC very easily. Next, shifting in S domain. Always remember that whenever there is a shifting in S domain or in frequency domain, we can see that the effect goes with the opposite sign. Okay. The effect goes with the opposite sign. So what is this meaning of this? So suppose we have x of t having the Laplace transform x of s. X of s minus s naught. So here the effect goes with the opposite sign. Here we have minus s naught, so here we will have plus s naught. Plus s naught t. Suppose we have x of s plus s naught, the effect will go with the opposite sign, xt e to power minus s naught t. So these are the properties. We don't need to worry about the ROC because for ROC we only need to know the format of the time domain signal and location of the pole, nothing else. Great. So differentiation in time domain. Differentiation in time domain means the property is very useful. If xt is having Laplace transform x of s, so if we differentiate it with respect to time, then we'll multiply by s in the Laplace domain. Multiply by s in the Laplace domain. So differentiation in time domain means simply multiply by s in the Laplace domain. Great. Next is differentiation in s domain. This property is also very useful. For example, xt is having the Laplace transform x of s, then t times of xt, if you multiply t here, then the property will be minus d by ds x of s. Okay, so these are the properties of the Laplace transform. You all have to remember the properties, otherwise you won't be able to solve the questions. The last property is convolution in time domain. The property says that if x1t has Laplace transform x1s and x2t has Laplace transform x2s, then x1t convolve x2t will have Laplace transform x1s multiplied by x2s. Now this property is very useful for convolution of the signals. Whenever we want to convolute the signals in time domain, then we actually multiply them in Laplace domain and perform the inverse Laplace to get the signal or the result. Okay, so these are all the properties of the Laplace transform. Okay, so I have clubbed all the properties here for revisions. Okay, so all the properties are there for the revisions. So I would request all the students to revise the properties, write the properties, make it chart, and we'll be solving the questions in the next class. Okay, in the next class, we'll be solving the questions, we'll be completing the inverse Laplace, and we'll also be completing the system analysis using Laplace. So thank you, dear students. This is all for in this session. We have completed the properties, we have completed the concept of ROC, and the next session we'll be doing the questions and system analysis also. Thank you.